to call on Stephen to give us his presentation on what makes an engineer. Stephen?
Oh, thank you very much, Bob. I really look forward to doing this, giving this presentation today. I want to thank ASCE for the opportunity. This actually started out as a 4-hour workshop a number of years ago at an ASCE conference. I've actually added some material to it, but I have taken out a lot of primarily examples. So we should have a good amount of material today to discuss. Understanding engineering due diligence and engineering judgment is something that's really meant a lot to me. But I think even today, I want to answer the more fundamental question about what makes an engineer, or to be more direct, let's see, I got to get my screen to advance. Hold on. Let's see. There we go. To be more direct, are we really engineers or just technicians with PE licenses? And what are the characteristics that distinguish us as true engineers? The learning objectives, I've actually modified these. They're slightly different than what was published, I think, to be more comprehensive of what we're looking at today. It's to help you recognize your responsibilities and obligations as a professional engineer, to avoid some of the traps that lead to a failure of due diligence, and to understand the role of engineering judgment and to apply it in the practice of engineering. The first thing we're going to ask is, what is engineering? I want to credit an article I ran into several years ago called Engineering Thinking and Rhetoric. I do want to say that I've got a bibliography at the end of this presentation, and I have made a PDF copy of the presentation available to share, and it will be distributed when your PDH is distributed. But when you ask what is engineering, fundamentally, engineering is solving problems. It usually involves designing and building artifacts. It applies science and mathematical principles. It uses abstract and physical models to represent, understand, and interpret the problem, as well as potential solutions. Engineering applies well-established principles and methods. It adapts existing solutions. It uses proven components and tools. It seeks good and, if possible, optimum solutions according to well-defined criteria. Engineering is more than math skills, scientific knowledge, or technical proficiency. In fact, John Robinson concludes that engineering's goal, problem solving, and its method, deduction and analogy, is much closer to medicine and ethics than to science. And I think understanding what we do in terms of how doctors do things in their practice of medicine may help us get a better understanding of how we use judgment, how we use due diligence. I'd next like to talk about what I call 5 essential characteristics of an engineer. We could have discussions together, probably we might come up with 7 essential characteristics. You might come up with 4. You might come up with 5 that are different from mine. So this is definitely not a comprehensive list, but in my experience, these are 5 essential characteristics that I've run into that I think need to be addressed. They are, and we'll look at these in more detail. Engineers provide solutions to real problems. They know the limits of their competence. They exercise judgment. Engineers must tell the uncomfortable truth, and we are needed to meet the challenges of a changing world. So let's look at this. Engineers provide solutions to real problems. Solving equations and following regulations are not ends in themselves. Models are only a tool to develop a solution. And we really need to be aware of the regulatory environment. merely following permit requirements, design standards, and regulations is not a substitute for good engineering. Unfortunately, a lot of our problems start early on, even back when we're in engineering school. A lot of times principles and formulas are shared, and then there's homework problems to test whether or not you have been, you understand the principle and the formula. But the homework problems will have something like neglecting air resistance. Or if you're doing anything with hydraulic head, it's assume a column of infinite height. Unfortunately, doing drainage project review, I have seen at least 2 instances in my career where an engineer wanted to show for some reason that a 24-inch pipe could hold 60 or 80 CFS of water. And the only way you could do that was within about 25 feet of head on that. So they showed 25 feet of head, but that would have put their whole subdivision or their whole project completely underwater. And I didn't see a guy build a big boat or the animals matching up 2 by 2. So I kind of decided that that was probably not a very realistic determination. So in order to do that, John Robinson says that for engineering students, rather than learning to follow or to solve problems by following a generic recipe, students should be learning to solve problems by getting as much information as possible on analogous previous problems, their solutions, their solution processes, and then applying this information skillfully. In other words, we need to learn the whole problem-solving process and not just the formula application process. They're completely different, and applying a formula might not necessarily provide a solution to a real problem. Second, engineers need to know the limits of their competence. We have an increasing body of knowledge today. We have increasing dependence on computer programs and design guidance. And while using these tools may help us deal with more complex conditions, they can also become a crutch which provides us with a false competence. For example, just because I know how to do, I learned in engineering school how to do Kai pipes doesn't make me qualified to design a municipal water system. A quote I found, operating in our competence zone is doing what we know and knowing what we don't. If we have a knowledge gap, we know how important this is to reaching our goals, and then either get smart or find someone that can be smart for us in that particular area. Very, very early in my career, I found myself faced with designing a jet fuel fueling system. The 2 people in the company who had worked on it previously had both left. It fell to my lap, and it was basically up to me to figure out how to do it, and I had absolutely no background in that. But I did the best thing and a good engineer knows how to do if he needs to get smart. I went and looked at all the other jet fuel fueling systems that I could find for helicopters. This was actually for the Fort Worth Police Heliport, so it was very, if it had not functioned properly, it would have been very high profile. But those are the kinds of things sometimes we have to quit, not worry about what our project budget is or something like that. If it's very important to get it to reach our goals, then we've got to find a way to get smart, because very few companies want to go find someone else to be smart, sub it out to someone else. Everybody wants to keep it in-house, and they somehow always want to keep their existing staff to figure it out rather than even look for the experts in their company. When we work outside of our competence, it often leads to undermining our profession. It can lead to alternative certifications. Some of them can be regulatory, like the asbestos management planner in Texas, or the corrective action project manager for leaking petroleum storage tanks. Or they can be voluntary certifications, such as certified professional or a certified floodplain manager, or a certified professional in erosion and sedimentation control. But all of these alternative certifications basically threaten the integrity of our PE license. And in some states, that has actually been under threat from legislators. The next point is that engineers exercise judgment. We're actually going to have a whole section on engineering judgment, so I just want to touch on it briefly. One quote I ran into: an experienced engineer applies his or her judgment to try and ensure that solutions will really work in practice, allowing for the assumptions, variations, and uncertainties of practical systems. And also, engineering judgment requires that we use our skills and professionalism to bring about good solutions that recognize the realities of their business context. So we ask the questions: is the proposed solution practical? Does it meet the client's needs? Is it affordable and cost effective? Does it meet appropriate standards of safety? And perhaps maybe more importantly, does the solution satisfy the applicable engineering principles, even if it deviates from standard design? Remember, at one point, there was somebody that built the first truss bridge, somebody that built the first cable stayed bridge. The first highway designer that put a one-lane road over on a 30-foot bent to go over another road at a skew. So those are all the kinds of things that had to be done the first time. And so people, said, well, that's not in standard design, but yes, but it did follow the applicable engineering principles. And those are the kinds of things that lead to good innovation in engineering. The fourth one is that engineers must tell the uncomfortable truth. Before we read this, I want to introduce you to Roger Bias-Jolly. He was an engineer with Morton Thiokol who worked on the Space Shuttle's solid rocket boosters. And he was one of the first engineers to identify that the O-rings might be a problem. This was a full year before the Challenger disaster. He had, in fact, recommended that very adamantly recommended that the shuttle not be launched that morning when below freezing temperatures, that the ice crystals could actually open up more openings in the O-rings than they were already present. He was overruled, and in the subsequent investigation, rather than hiding all of the stuff that Morton Thiokol wanted him to do, he became a whistleblower. Of course, he was not allowed to be fired, but that didn't mean he didn't end up with some dead-end work for the rest of his career there. So Roger says, all of you must now evaluate your careers and emerge with the knowledge and conviction that you have a professional and moral responsibility to yourselves and to your fellow man to defend the truth and expose any questionable practices that will lead to an unsafe product. And then another quote I found: engineers have a responsibility that goes beyond the building of machines and systems. We cannot leave it to the technical illiterates or even to literate and overloaded technical administrators to decide what is safe and for the public good. We must tell what we know. We need more critical pronouncements and published declarations by engineers in high professional responsibilities. In some instances, such criticism must be severe if we are properly to serve mankind and preserve our freedom. Unfortunately, I couldn't find where I found that quote from Adolf Ackerman several years ago, but I did a little research. He was a member of ASME, he was a member of ASCE, and back in the 40s, the 50s, and 60s, he was a very strong advocate for engineering ethics. And I'm actually interested in looking up more of his work. And then finally, engineers are needed to meet the challenges of a changing world. We have changing technology, changing regulations, changing expectations, And what I've heard is the term VUCA. This term actually first arose, was more widely used actually in West Point in the late 80s, but it's more broadly been used to describe business context today, everything about our society today. We experience volatility, uncertainty, complexity, and ambiguity. And for those of us older engineers who either remember directly or remember stories about, what life in the engineering field was like in the 50s, 60s, and 70s, it was a whole lot different than it was today. Everything was more straightforward. Of course, there were much fewer tools available. There were much greater certainties, even if those certainties ultimately proved to be wrong. But it was a much simpler and straightforward situation. And today we just don't have that in this world. And to respond to all of that, engineers basically need to stand up and be leaders. And I do have a whole separate lecture on engineers as leaders that we will not get into today. So now let's talk a little bit about engineering due diligence and what it means. It can be a standard of thoroughness by which a job is executed to completion. Someone said all reasonable practical precautions are in place based on the balance of the significance of the risk versus the effort required to achieve it. Going back to our original article on engineering thinking and rhetoric, John Robinson said, getting something to work is inadequate. It has to work well according to parameters of the problem. Even in simple problem solving, the engineer looks for evidence that the space of possible solutions was properly searched and the chosen solution correctly proved to be optimal. Let me give an example. Local design guidance. Folks who use that, engineers who use that really must know and use the design guidance well. Much work went into developing it. Don't embarrass yourself with ignorance. Well, down in San Antonio, this is how they do it. Well, you're in Austin now. It's got different. Or in the Metroplex, well, Dallas does it this way, or these Dallas suburbs do it this way. Well, Fort Worth does it this way. Well, know what community you're in and what the design standards are. And do not ask a reviewer, what do I need to do to make you happy? My happiness when I was reviewing was not at issue here. It was the safety of the public. It was the practicality of the solution. It was how, whether our maintenance standards were adhered to. I had a co-worker in another department. He dealt with consulting engineers a lot. And he had this sign on his office: if talking to me is an alternative to thinking, please go away and think. Well, the folks in my department thought that was probably not appropriate for somebody who dealt with the public from time to time like I did. So I wasn't allowed to have that sign in my office, and that was probably a fairly good idea. But you understand, reviewers are really tired of people saying, well, I don't want to go read all the design guidance. Just tell me what I need to do to make you happy. We've got to beware of using engineering crutches. Design manuals can sometimes be idiots' guides, but we've got to be more than the idiots. We've got to make sure we're understanding the underlying principles. The minimum standard does not necessarily mean it's a maximum standard. We had an engineer in Fort Worth who practiced for years that we had a minimum standard of a 60-foot open channel easement. And I swear he would have found a way to fit the Mississippi River in a 60-foot easement if he'd ever been presented that challenge, because he just did not like giving up any more land and losing any more lots in his subdivision than absolutely was necessary. Know that engineering software is no substitute for knowing underlying principles. The more and more we use complex engineering tools today, I think that's becoming more and more of a challenge. And generally, when you see the words contractor shall on a set of plans, it usually means the engineer doesn't know how to make it work. One note I saw on a set of plans was adjust existing handrails to be ADA compliant. Well, that really told the contractor an awful lot about what he needed to do do that. So generally, contractor shall means engineer doesn't know how to make it work. And when we talk about using, design manuals or design standards, we had a situation. We had a 14-foot drop inlet. It actually had 12-foot openings on the side. I think we had quite a bit of overland flow coming, but it was going to be sheet flow, so the drop inlet was decided to be used. But I got to looking at it. It was also over a rather large box culvert. But I got to looking at the design, and it showed that it only had a 6-inch thick slab with one row of number 4 bars at 12 inches on center. And I asked the engineer about that. He said, well, it was designed for pedestrian loading. After all, it's off the street. Because who would really consider using a large inlet top for a vehicle work area? You know, certainly not an engineer who was designing by the book. But obviously anybody with practical experience knows that things are used for all sorts of things they were never designed for. Now, I'd like a brief example here for engineering due diligence. What tasks are required to prepare an engineering design for a public works project? This is a question that you would ask very first off when you're trying to prepare a bid proposal. Let's say you've been selected for a job. Maybe it's not, I won't call it a bid proposal, but you're coming up with a fee schedule. Well, to come up with a fee schedule, you've got to identify all the work items that you've got to do. So take a couple minutes here while we're talking about this. Think of what are some of the tasks that are required to prepare an engineering design. This is actually better suited for workshop, but I think we can do it. If any of you want to write them in chat, that's fine, or if you just want to make a list at your desk. Here's some that I pulled out from existing workshops and some of the work I've done before. You've got survey and control, geotechnical investigation, subsurface utility engineering. Many projects you have hydrology and hydraulics. You may have maintenance records review. A lot of public projects, you'll have public meeting and stakeholder input. You may have design criteria evaluation. You may need to look at utility relocations and pavement repair if you're putting anything subsurface. Some construction method evaluation, maybe materials evaluation. Do I use ductile iron? Do I use PVC? Do I use something else? Special construction details. Make sure to include QA/QC efforts. Constructability review. Please spend time on bid quantities. We're going to get into that in a little bit. You've got to have time to develop an opinion of probable cost. You've got to prepare the specs. You've got to secure the permitting, or at least identify the permitting to be secured. You've got a traffic control plan, erosion control and SWIP, stormwater pollution prevention plan, construction inspection or oversight. All of these things may need to be considered at some point or another. There may be some other things too that are left out, but these were 2 full slides, so we're gonna stop there. So now let's talk a little bit about some common failures of due diligence. And I'll give you 5 subtopics here we're going to look at. No time in the field or using the actual product. You don't think through how things are built. Rushed, sloppy work. and one I'll just call full steam ahead. We'll look at that. And then giving the client exactly what they ask for. No, that's not necessarily a nice gift. That may actually be a failure of due diligence. No time in the field. More and more I'm seeing, I found that engineers seem to trust surveyors for site information. And I found out there's many foreseeable, unforeseen site conditions. I was actually doing some project management work, and we were developing risk registers. And we started looking at the TxDOT risk register that they've developed for their projects. It's several pages long, but there's quite a number of unforeseen this or unforeseen that, things that were very foreseeable. And sometimes it's not even knowing how things are built if you don't have time in the field. Now, why don't engineers spend time in the field? Well, all of them think that this is what it's going to look like when you go out and you look at a culvert pipe. I've been out in the field for most of my career. I have seen an occasional snake in the grass, typically running away or slithering away from where we were working. I've never seen this anywhere but this one particular slide. This was actually the background of it. This was not even a pipe in use. This was a pipe that had been stored for a long, long time out in a field. So, you know, don't be afraid that just because you go out in the field, you're going to see things like this. So what do I mean about foreseeable, unforeseen conditions? We had a set of plans, didn't really catch this until the plans were already under construction, but we were upsizing a 48-inch or a 24-inch line to a 42-inch line, and trying to better protect one neighborhood, and it came down. And so they ran into a 24-inch line, RCP, outfall unknown, no plans exist. So the question is, as it got under construction, we realized there was going to be some issues. So did anyone look for the outfall unknown? Well, you can see if you look down there, the slope is heading down to those trees. But you can't find it sitting in the car. You can't even find it from the parking lot. But if you go down a little bit, is that water I see? Well, you follow the water upstream and you find a partially submerged head wall. Well, there it is. So the reason that was important is because they had let the inlet be the overflow from 42-inch pipe going to a 24-inch pipe. But unfortunately, it was overflowing right into a building. We caught that before the construction was finished, and we had them then upsize design while everything is on hold, go back and design 42-inch pipe extension all the way down to the outfall, down behind that gas station. Here's another set of plans I ran into. This was a subdivision being built. I'll say this is about 20 years ago. They did extensive topo work on their site, and they even did topo work on the site of the electrical transmission right away next to them. They got permission from the transmission, the utility, and were able to build that storm drain. And it just kind of stops like it's on the edge of the earth. It reminds me of what everybody thought of back in the day of Christopher Columbus, that somehow everything was going to fall off the edge of the earth. So I had the engineer, I said, well, where does the water go from here? Well, they pulled up a 1964 topo, and it showed, okay, they're going into a drainage draw on the next property over. I said, okay, that looks fine. But this was, of course, early 2000, and a screening levee had been built in the early 70s and had been there. This was actually a concrete quarry that it was outflowing into. And so the levee was there to protect from view all the quarry work. Well, the contractor and inspector both agreed that this thing needed to drain. So the storm drain outfall was cut through the levee by trespass. due to the engineer's failure to verify site conditions. The engineer never went out on site to look at this. Never looked to see that there was a screening levy. Well, it turned out that there ended up being a legal settlement between the property owners. I was told it was in the six figures. Knowing what I know today and figuring out how prices have risen, I wouldn't be surprised if it wasn't something like this happened today in the $250,000 to $500,000 worth of settlement. Just, you could go get permission for a whole lot cheaper than you can get trespass and legal settlement after the fact. Sometimes permission is cheaper than forgiveness. It was another set of plans I looked at. I'm sure that on the CAD screen, all of these things were different colored lines, but I always hated looking at these sets of plans and you're trying to figure out what line belongs to what. But it was a new subdivision going in. Cook's Lane was an existing roadway. They upsized the existing line under Cook's Lane, and then that was part of their drainage system as it went on down through their subdivision. They sized this subdivision again, a very, very busy drawing, difficult to read. But they're doing their drainage area map, and you see 590, 595, the top is at 600, 595, 590. But the way these lines are drawn, that just doesn't exactly look right. That there's, somehow a ridge at 600. And you look over here, and there's 600, 605, 610. And it turns out that these were mislabeled, probably by the surveyor. And this was really not even up at the top of the hill. So we did some more investigation and determined the actual watershed was about 3 times the size of the watershed that they shown in their particular drawings. And it ended up affecting the culvert size, and they had quite a few remedial, I don't remember all of the remedial things they had to do, but it was not a cheap solution. And in our investigations, we even looked at the adjacent watershed. We had 1978 storm drain plans, and their watershed is shown in yellow, which pretty much matched up to what we had in red. And of course, no time in field, you see projects, you don't see projects after Mother Nature gets to them. I've talked to engineers on several occasions where they said, well, we've done this, for years this way. And I said, well, have you ever gone back to your projects 2 or 3 years after they built? This was a channel that was about 2 years old. That's a sewer line. There was a concrete cap on the sewer line to keep it from being eroded, but the erosion had actually gone all the way under. There was actually at one point a 6-foot deep scour hole there. There was another line. The channel was actually supposed to be up at this level. Here was another one, again, 2 or 3 years after construction. You see the pipe in the background. Our best guess is that the existing ground was in red at one point, had the little flap gate, but a huge amount of erosion, because nobody had really bothered to look at, how stable. That was actually dropping about 15 feet down into another creek, and Mother Nature doesn't like those steep waterfall drop-offs. She's trying to get a more stable grade, and of course you end up with this kind of erosion. Another fear is you don't think through how things are built. Just because you can draw it doesn't mean it can be built. Just because it can be built doesn't mean it's sustainable. I've actually seen a situation where somebody was trying to drain a field. The water used to run over the road, ran through a small culvert, but they're building a subdivision on the other side. So they're trying to get it all to go to one point. And they were trying to put an 8-foot deep bar ditch about 4 feet off the edge of the road. Well, you could probably build it but that wouldn't mean that the road wouldn't actually be caving in within about a year or two of that having been built. And then don't fall into the trap of using center lines and midpoints. You know, we do designs and boy, you know, we can snap to the center. Everything looks so symmetrical. Here we have in storm drain inlet. We've got a pipe right in the middle of it. We've got goes right down the property line. There's an easement on both sides. Well, first of all, in Fort Worth, you've got to put the pipe tying into one of the inlets. Fort Worth had a requirement for a 2-inlet manhole. So the pipe had to go in, so that way our cleaning trucks go in and go through the manhole and clean the line. And you don't want to put a pipe right down under the center line of the property. Otherwise, you might end up with something like this. Don't know what kind of pipe it was, don't know what kind of machine they used to put those fence posts in, but obviously we want to avoid having these kind of problems. Rush sloppy work is something I've run into a lot. It can be people trying to get comments cleared without doing the necessary rework. It may be a lack of QA/QC. One of the things we ran into an awful lot was incorrect quantity. Somebody finally got done with the design. They're trying to hurry up and get the project out. So the last minute deal is, let's count up the quantities, put together our OPCC. Oh, we got to hurry up. We don't have much budget left. Let's just throw together the specs. And it ends up as change order nightmares. Now, when I was first presenting this, I actually had 2 or 3 specific projects, and I tried to change the names. But the person I was working with, she was over these projects. She said, no, we need to make them far more generic than that. So I finally said, well, okay, why don't I just make this consolidated case study? This will actually be things that happened at over 2 or 3, maybe 4 or 5 different projects, but we'll just call this a Hades drainage improvements project. So, but again, this is not a single project that this happened on, but for the sake of protecting both the guilty and the innocent, we're going to consider this as a kind of an umbrella type project. On one of these projects, we had multiple PM changes during the project. Overall, the project starts to drag out. Well, then the city becomes overdue on its commitments to citizens. And in order to satisfy that, the project was rushed through one phase of design. Unfortunately, that ended up being a very complex phase with several specialties. And I have to say the city cut consultant fees too drastically. And that's both on the consultant for not identifying all the work that really needed to be done, as well as on the city for everybody always wants to get something for nothing, and cities are probably some of the worst. And then the change of project managers exhausted the project budget. I think many of us have been there in our careers. So, you know, how do you spell disaster? Well, here's some of the issues. Our engineering design issues, we had unique features that were designed by the book rather than by an engineer with specialized experience. In one case, we had each new project manager second guessing the prior design decisions. And on one of our projects, the final project designer was a young EIT. He was still in high school when the project had begun. And I called him project designer because the PM actually didn't know any project details. And he was called the final project designer because consultant contract was terminated after we ran into that situation. We had project management coordination issues where the lead design engineer is doubling as a project manager. So he's trying to perform design as well as coordinate project parts. Well, each designer considered their specialty to be most important, which led to conflicts. We had a planning plan that put trees down the middle of an unpaved maintenance road because we were trying to put as many trees back on site as possible to mitigate tree loss. And the set of plans didn't show edge of a roadway or anything. So the person working on that thought, here's a nice wide open flat area that I can put a lot of trees on. Similarly, the irrigation system was designed by a landscape architect, but the project manager did not notify the electrical engineer to provide power to the control box. So now you can imagine construction issues. These are just 3 of the big quantity errors that we've ran into over various projects. Sidewalk, the engineer was less than half of what was in the project. Articulating block, less than a third. And fill material, the engineer had actually counted up less than 25% of the actual fill material that was in his own design. And that was a huge, huge quantity. Well, in many cases, the contractor is working at risk to install extra quantities while the change order is processed. In the case of the electrical system for the landscaping died and the weeds grew, waiting on the design of the irrigation electrical supply. It was ugly. It was a terrible, we had a lot of landscaping there because it was going to be in a very public location where it could be seen. And of course, it was a public relations nightmare with the site abandoned and Johnson grass growing and all the planted landscaping dying. There's another failure that I would call full steam ahead, where you make assumptions early in a job, you never revisit their validity to much later. These can result in unwanted or infeasible solutions such as route selection, construction method, design criteria assumptions. It's like climbing way up a ladder before checking to see if it's leaning up against the right house. And unfortunately, the only way to rectify it is to go all the way back down to the bottom. I'll give you one example. We were upsizing a storm drain system. It was agreed that building a relief system would be cheaper than trying to upsize the existing system. The engineer, the modeler for that engineer wanted to get started on the model, so he assumed an initial alignment to start modeling. Nobody ever second guessed that. They went through extensive design effort. They never reevaluated the alignment. If you turn on the topography, you see that it's actually going up a hill. Ends up happening that you have a section that's 20 feet deep. And in a residential neighborhood, that was just, with other utilities in the street, that was just going to be way too deep to be practical. But if they simply reevaluated the alignment and chosen the alignment in green, they would have found standard covered the entire way. Would not have presented any issues at all. And you may be, also unwilling to consider a non-standard approach. Albert Einstein said insanity is doing the same thing over and over again and expecting different results. General Patton said, if everybody is thinking alike, then somebody isn't thinking. I'll touch on this real quickly. Ran into a situation where we had a neighborhood flooding. As the floods got worse, the damage got higher. The actual system was only about 1 inch an hour. But if you went and looked at it on an annualized basis, all of the damages were down here in this lower end. If you go back to industrial engineering, I think we used an I of 7% and a return of 50 years. And they engineer determined that the existing damages was $36.5 million. But if we focused on where the damages were occurring, and we put in just raise the system from 1 inch an hour to 2 inches an hour, no, it wasn't anywhere near the city standards of 100-year for new development. It wasn't even a 5-year standard, but we were reducing the damage in that neighborhood from the net present value from 36.5 million we were actually eliminating $29 million of it. And so the residual damages was $7.5 million. So sometimes, you know, if you're trying to make life better, if you can't make it perfect, you always make it better. And you come up with things like this. Another way, thinking outside the box, a remote Chinese village was trying to get access to the outside world with anything, with something other than pack animals. And so they actually, you know, worked on building their own tunnel system through the adjoining cliff system. Very innovative, certainly not something that, you know, most engineers would think of as a valid solution. Finally, giving the client exactly what they asked for. You didn't really evaluate the stated scope of work. You know, the client said he needed this done. You try and cheapen a project because the client doesn't have enough money, and generally no good deed goes unpunished. But it doesn't matter how good a job you think you did if the client's problem is not solved, or if your solution is unaffordable or impractical. And, you know, and I asked for solutions. I kind of thought through some things, but I hadn't really worked through the project details. And sometimes I had things that were not practical, and would rather have had the engineers, the consultants, tell me that they weren't practical instead of designing the way I thought it would go. If I had all of those resources, I wouldn't have needed to hire them. So I really, even when I asked for things as a project originator, I needed them to think through the details and go back a different direction if the solution I thought of wasn't practical. We've all seen this, what the owner ordered, how the architect designed it. He liked symmetry. Engineer always wants the factor of safety, so that's how he designed it. We know how the contractor will want to bid it. And of course, the contractor actually installs it something like this. And that's what the owner really wanted all along, but maybe didn't communicate it very well. I want to briefly touch on a study where over 11,000 feet of high density polyethylene pipe collapsed, was replaced with RCP. This is not a pipe issue. It was actually an engineering design issue. They ended up paying over $3 million to Texas Parks and Wildlife Department, and over $200,000 to the contractor. Well, the forensic analysis said that the external forces imposed by soil and hydrostatic pressure exceeded capacity of the pipe. There's those words, should have been foreseen, because geotechnical studies were available. The engineer designed the pipe solely by using a chart, even though the chart did not account for the groundwater. That's what happens. You're trying to save the client money, so you're using your EITs to do most of the design. EITs, you know, well, you stick a chart in front of them, tell them, you know, design it by this. And, you know, the engineer should have more carefully chosen the type of backfill and degree of compaction. I heard this from Danny Kaler at at CECon back about 10 years or so ago. Cost pressures cause business leaders to make short-term financial choices at the expense of public interest and or long-term financial sustainability. Clients and facility owners risk far more financial loss due to poor engineering than savings due to cutting corners. Engineering judgment. We're going to, I know we're running short on time. Sometimes this presentation takes an hour and 15 minutes, and sometimes I do it in 50 minutes. So we're going to try and shorten things up here and get done on time. Engineering judgments, forming an opinion or evaluation which conforms to the technical and ethical standards of engineering by discerning and comparing. It's developed through our training, our experience, our professional development, and all too often by our mistakes. In fact, a man being honored for his success in business was being interviewed. What's the secret of your success? Good decisions, he said. How did you make good decisions? Experience. What kind of experience was that? Bad decisions. Um, but most of us, a lot of us have had enough bad decisions in our past, or we've learned from folks that have told us about their bad decisions that have helped us make good decisions. An experienced engineer applies his or her judgment to try and ensure that solutions will really work in practice. This is going back to our quote from John Robinson earlier. Getting something to work is inadequate. It has to work well according to the parameters of the problem. Even in simple problem solving, the engineer looks for evidence that the space of possible solutions was properly searched and the chosen solution correctly proved to be optimal. Another way to put it is that bad engineering judgment includes the application of rules of thumb without consideration to how they were derived, hence not understanding when they're invalid. While the rule may be right 90% of the time, someone who has no feel or engineering judgment will only get it right 9 times out of 10. Good engineering equates to good business, meaning that the output has to work not only technically, but in an organizational or commercial context. So this requires that we use our skill and professionalism to bring about good solutions that recognize the realities, again, of their business context. You know, the solution's got to be economical. It's got to be cost effective. Some key points is using formulas, design guidelines, making careful calculations, and building models, however complex, describes the work of a technician, not an engineer. An engineer may do these tasks, but his or her responsibility does not stop there. An engineer must first understand the problem to be solved, then must develop a solution process that will lead to a successful solution. He or she must then evaluate whether design guidance or a standard solution is appropriate, or how either should be modified in order to solve the problem. An engineer must understand the principles and limitations of any model developed, and must apply model results in an appropriate manner to solve the underlying problem. He or she must similarly evaluate whether any of the other tools used have been properly applied. The engineer must then answer, does the proposed solution provide a complete solution to the problem? Have design deficiencies that may lead to failure been identified and addressed? And is the solution feasible and affordable? Only then is a solution complete and ready to be sealed and submitted. In other words, don't depend on computer programs to the detriment of common sense. Don't let design standards blind you to the economics. If we'd done that, for example, we could never afford a 100-year system, so we would have let that neighborhood continue to flood, no matter how bad the damages were. You don't want to jump to the immediate or obvious conclusions. You want to think things through. And the problem statement really is not build this, but solve this problem. And with my apologies to the trained philosophers, a little Plato to go with Aristotle. Aristotle used inductive reasoning, inductive logic, build from the ground up. A little Plato is his deductive reasoning. You start with the big idea and you work down to the solution. And finally, in closing, here's a quote. This is actually, Dr. Goldman was doing this on a TED Talk. In med school, I was obsessive compulsive and I did very well and I graduated with honors. And I came out of medical school with the impression that if I memorized everything and knew everything, or as much as possible, as close to everything as possible, that it would immunize me against making mistakes. And it worked for a while until I met Mrs. Drucker. Then he went on to describe Mrs. Drucker as being the first person that he misdiagnosed and who died as a result of his misdiagnosis. And he goes on to further talk from there. And responding to that, I found a quote from an engineer in England. The quote above will hopefully kickstart some reflective thoughts on whether we engineers have what it takes to assume the mantle of technical and social responsibility that we shoulder. Here are my sources. We don't really have much time for questions today, but you can contact me, and I would be happy to answer those for you. I will be at CECon next month. I hope to see some of you there in San Marcos. With that, I will turn it back over to Mike.
This is Bob, Stephen. Just
Or
a
Bob, okay.
couple quick questions. Is the engineer's job to do a perfect design?
What's that?
Is the
No,
engineer's
obviously not perfect. If I heard the word right, perfect. No, nobody can be perfect. And a perfect design does not recognize its business, its context. One example I'll give you, there is no perfect safety system in a car, but do we still put seatbelts in cars even though they're not perfect? Yes, we do, because that might save 95 or 98% of the lives that would otherwise be lost, or avoid a lot of significant injuries. So we don't look for perfect solutions. We can't afford perfect, but we've got to look at something that is at least optimal, or at best optimal, and at least does solve the problem.
Well, that kind of gets to the answer to the next question that we have here is, when doing a design, how do you know when to stop trying to improve it to lower the cost?
Well, at a certain point, you've got to decide this is the design you're going. And I will say that I ran into this the first time I was sealing a set of plans, and wasn't changing the design much as I was trying to get all of the, I was updating all the notes on the project. It was a sanitary sewer project. And so if I have updated stuff on how this manhole worked, I needed to make consistent notes. And I swear I blew a good part of the project budget just because I knew this was the first set of plants I was going to seal. And that's where engineering judgment comes in. There's a certain point that due diligence becomes excessive diligence. And, that's why we call it due diligence. There's a certain amount that you've got to stop. And ultimately you need to have a senior engineer who's been down that road before say, this is as far as we go and no further.